Good morning, good afternoon, and good evening, everyone. My name is Priyanka, and I am the executive at International Bauxite Alumina and Aluminum Society. Today, on behalf of Dr. Ashok Nandi, I welcome you all to the IBAAS JNARDDC Technical Lecture Series 2022. Today's lecture will be presented by Mr. Marc Dupuis. Marc Dupuis is a consultant who has specialized in the applications of mathematical modeling for his own consulting company, GéniSim Inc. And the topic of presentation is review of 50 years of Hall-Héroult cell models development. If you have any questions during the presentation, please drop them into the chat box. I will bring them up after the presentation. Now, without further delay, let's start the presentation.
Welcome to this fifth webinar organized by IBAAS and the JNARDDC. I'm Dr. Marc Dupuis. I'm working for my own company, GéniSim, And for Hatch Engineering Company, I will talk about the review of the 50 years of the Hall-Héroult cell model development. About myself, I've been working in the aluminum industry for the 40 last year. So 40 out of the 50 years I'm gonna cover. So I'm working for my own company and part-time for Hatch. And I've been developing those kind of models, as you will see in my presentation. So about the background that you see for my presentation, it's from my very first trip to India in 2002, so exactly 20 years ago. And I was, that's me being welcome at the Pride Hotel in Nagpur. And then I'm visiting this garden where this bridge is located. So the Ambarazi Garden in Nagpur. So that's me here on the bridge. And I've been there for participating to the so aluminum electrolysis seminar organized by the JNARDDC 20 years ago. And here on that picture, the head table, you can see three of the director, the very first director, Dr. Ramesh Chandra, and then the then current director, Dr. Kutumbarahu, and then the recent director, the future director at the time, Dr. Andrine Otri. For me, it's Anipan. Sorry about the pronunciation. So that's that's me presenting a paper about modeling at that conference. And if you look carefully about the models that are here on the screen, you see that they are the same here. So my company, GéniSim, is distributing those products, so that modeling technology for the Hall-Héroult cell. So this is the thermoelectric I'm going to present soon, and then this is the dynamic cell simulator, Dynamark, and this is the MHD cell stability code called MHD Valdez. And in 2003, I came back to India to train IBAAS using those thermoelectric models. In 2005, NALCO. And for Hatch is also involved with modeling a Hall-Héroult cell for supporting its activity in engineering. And here you have a pot room ventilation, and here a bus bar ventilation. And here you have a flex deformation model. So I will cover most of that kind of modeling in the presentation. So the full list of models I'm going to cover is here. So there's 14 of them. They are per order of importance, mostly. So thermoelectric, MHD, and bubble flow, alumina dissolution, multiphysics, up to CFD ventilation, thermomechanical, up to digital twin. So I'm going to cover all of those if I have time. Normally, I hope I will have to go fairly fast. Sorry about that. To present all this material, about 100 slides in 1 hour. So the first model is the cell balance model. So you essentially want to control the superheat and the ledge thickness indirectly, because it's a pot to just decide about those things. But you have to design the heat generation and the heat dissipation so that the pot will operate at a practical superheat of about, let's say, 10, with the ledge thickness about 4 to 10 centimeters. If you have too much, it's bad. If you have not enough, it's bad. Here it will create an instability, so it's bad for MHD, and here it's bad for pot life because there's not enough protection on the side. So historically, this is even older than the 50-year cover by the presentation in principle. It started by pioneer work by Warren Open in the 50s, and that's the type of code he was developing at the time, and that's the type of environment. So you have a punch card and you type the code in those cards, and then you read those cards for processing the program. that was the environment even in the 70s when I started doing some computational work. I was still using, this was still the way to interact with the computer in those years, in the 70s already, still. Okay, here this slide is presenting some equation I got from Warren Open when he developed this solid balance for Alcoa. Essentially it was dictating a flux direction of the flux, and then 1D flux in different orientation, and then he was computing the resistance that you encounter, assuming a one direction. So you have this material and then this material and the third material. So yeah, that's why you have a series of material to establish the global resistance, thermal resistance. So, but this is assuming that the path of the heat, and that's, you may be close to reality, but you may be sometimes quite wrong. So there's a limitation for this kind of approach. That's why after that you shift to a mesh and then some finite element, finite difference. In this case, it's a finite element mesh, and that was developed by Jay Bergerman at Alcoa for heat valve 2D. That was the next generation after the pioneer work of Warren Open. We have some detail how you treat the change of property from the ledge to the liquid. And this is a result from Alcoa. Still today, Alcoa is using this kind of in-house model developed by over the year, and instead of using commercial code. So they are limited because this code is 2D, but they are still using this code today. And me, I was a different, Alcan follow a different path. They developed this kind of 2D model in the 60s and 70s, but they asked me already in the 80s when I joined Alcan in the 84 after my PhD. I was asked to use ANSYS commercial code to develop a 3D model of here. In that case, it's an anode. So you have the real anode here. It's an Alcoa P155 anode with copper rod. So the mesh, and that's the solution after 2 weeks of computing time. Because at the time in 84, this kind of model was to the limited way you could solve. Because if you have to wait 2 weeks to one solution, it's not very convenient. Now the same model will solve on by any computer in a few seconds, less than 30 seconds. Okay, so after having developed the anode, I developed the cathode. Here I'm presenting an example developed in 89. Not my very first cathode slice, but I'm presenting this one because I'm showing here. It's a side broken, so it's not a point feeder. It's a side broken cell operating at only 50 or 70 kiloamps. And so you have the ledge. It's very specific to this kind of technology. And what's unique about this kind of model is that the ledge is, you convert the shape of the ledge as part of the solution. And here it's my very first corner, cathode corner, that was developed in 86. So that's really my very first corner model. And here you have a solution processed with the code called Patran that is more or less disappeared. And after that, it's evolved to go to the full a quarter of a cathode, including part of the anode in the liquid zone to get the current density in the metal pad in 91. And then when I start working for myself, so GéniSim, I continue to publish, developing bigger model. So this is the full cell slice. It is the most typical model for the main model you want to use to design a cell or retrofit a cell. Here you have a full cathode and bus bar predicting the ledge all around. if you couple that with this MHD values or a CFD code, you can have a heat transfer coefficient that depend on the flow. And so you have a irregular or non-constant a ledge that may get thicker or thinner according to the flow. And then you can continue to expand to get the full cell here. So we have the anode, the full anode, and the full cathode, and the bus bar. So I published that after this one. So in the late 2005, maybe around that time. That was always getting close to the limit of the computer I had available to me. And then very, very recently, I collaborated with H to improve or update this modeling technology to use workbench and space claim for the machine. And then improve the physics. Here I have the trench. And we have improved the way to converge or to solve for the throw on the cathode, the ledge. So those are described in paper presented recently. Okay, next type of model. So once we're done with the thermoelectric, the next physical challenge is to the MHD self-ability. And this is an example, visual example of what we're fighting against. You imagine this is the surface of the bat metal interface. So this is the surface of the metal pad. And this wave here for this bridge was the wind that created this motion. It amplified because the frequency of the wind was matching the natural frequency of that Tacoma bridge. And to avoid that, you have to change the ratio of masses so that the natural frequency of the bridge is not matching the frequency of the wind. And for cell, here you have the explanation from Murata of what is happening. And then the recipe essentially is to prevent the amplification of the wave by reducing the amplitude of the vertical component of the magnetic field. Mostly. There's also the current density in the metal pad, that is a secondary issue, and the metal thickness, the ACD. So I cannot cover the physics, but I will cover the modeling work. So the first thing you need to have to solving the self-stability is to know the current density in the metal pad. And this kind of work calculation was pioneered by Givry and was presented in '65. It's also involved a solution of a code developed with the old technology. So using punch card to write the code, and then the code was solving for a 2D network, electrical network. So you have around the block, around the anode in the back. You have a cathode block in the other direction. And you have the metal pad here in one direction, the short direction, and the long direction. So eventually, you go to full 3D, and you get the current density in the metal pad. But to get the metal pad current density, you need to solve the current density in the full cell and in the bus bar around. So it's more involved than only those, but that was the starting point. And that, if you read the paper, it's quite advanced for its time, for sure. And then the next thing after that, you have to solve for the magnetic field. So the pioneer here is Selly. He presented the paper in 75. And here you have the Biot-Savart to get the magnetic field at this position P from this part of conductor of a network. So you have to add the contribution of all the pieces of bus bar. And that's why it's essentially a summation here to compute the magnetic field to every point that you have in space that you want to solve. And that's not enough, because if you have a ferromagnetic like a pot shell, you have to account for its magnetization, and the magnetization will act as a shield. So the inside of the container is protected from the magnetic field generated by busbar around that container. So to account for this calculation, you have to, the simplest way is to use a dipole approach. So you represent the structure by a bunch of dipoles, and they will magnetize according to the magnetic field around. And so if you combine the contribution of those dipoles to the main contribution from the bus bar, you can get the magnetic field inside the pot, as was presented by Sally in TMS 75. Then you have to solve for the flow. So you need the current density that you have computed with the calculation of current density calculation. Then you have the magnetic field. And historically, they were done separately. So they were one code solving the magnetic field using some assumed current, and one code was computing the current density into the liquid zone, assuming sometime you hope the similar boundary condition, but not necessarily 100%. That was the weakness of having two codes to solve the same physics. And so, and the third code was the code to, so you compute the Lorentz force, and then you solve for the flow. And the pioneer was Urata 75, and then Moreau Ziegler and used the Moreau-Evans model to compute this flow here. And this is a solution from Urata on the left. So 75 and 81 for the pioneer work for the flow. And then me in the 80s, I was involved to update, to essentially migrate to a better computer. The code that was being used at the time, similar code, was called Dupuis, and he was computing the flow and the back metal interface. And this code came from Norway. So it was developed in Norway, and Alcan had access to it, and that was the code that was used in the 80s to solve the flow and the back metal interface. So that's a steady state solution that we are getting. Up to now, we are talking about the steady state solution. And me, I pioneer using ANSYS to compute the same thing. So if ANSYS was starting at the 1990, was offering an element to compute the magnetic field. So you could compute in the same model both the current density and the magnetic field. So to get the magnetic field, you get to have the ferromagnetics of the partial. You have to have all those conductors. You have to have the liquid zone could be in 3D. The remaining could be only 1D, two conductor that would provide a magnetic field contribution. But you need to solve in that area here in the cell. You need to solve the current density and the magnetic field at the same time to be able to get the Lorentz force. And to get the magnetic field, you need to mesh the air around, because the finite element formulation forces you to solve the magnetic field all around. To get the impact of the magnetization inside, you need to have the connecting media is the air. So you have to mesh the air. So you have the current density solution, you have the magnetic field solution. And from that, you can compute the Lorentz force. So that's the Lorentz force here. And the Lorentz force ANSYS could not do anything with that. So you have to shift code. So me, historically, I use FIDAP. That is a code no longer much available. But that was a finite element code available at the time. So you import the mesh and you import the Lorentz force to FIDAP, and then you could solve the flow. So that's what I did in that work presented in 93. So this approach is still used today. So I will present other solutions similar with more recent, so with a better mesh. So you have the air again. You have the detailed geometry of the pot shell and the inside of the pot. You have conductors that are represented with line conductor, so 1D conductor. And you have the mesh for the liquid zone that you will transfer to CFX in that case. So the ANSYS is still used to compute the Lorentz force. And then you transfer the mesh and the Lorentz force to, in this case, CFX. That is a code also supported by ANSYS company to solve the flow inside the cell. And here you have the magnetic field that was calculated and the flow. So this work was done by KIT. There's a group in Brazil, and then more recently in China, Northeast University. They have used the same approach to ANSYS CFX combination to study the impact of those perturbation or irregular cathode technology that was for some time popular in China. So you have the geometry of the model here. You have the real thing here, and here you have the impact of those irregularity on the cathode surface that affect the current density. But the purpose of those is to slow down the flow by introducing a resistance to the flow, and it is working to a point. So this is the best modeling work that was published in Metallurgical Transaction B 2016. You can see that the flow B is with those perturbations. So the flow intensity is a bit reduced, and then the displacement is a bit reduced also. If you look at the same scale for both or about, but they are a bit less. So in principle, it is helping. It's marginal, as I published myself, and it's not lasting long because you have erosion. So even if it's could be considered like a good thing to have those irregularity to slow down the flow, because it's not lasting more than a year before the erosion remove all those things. It's less popular now, or not at all used anymore. But I showed that you can study those things in model. And the most recent work was published by Hall-Héroult Aluminium. So they combine ANSYS with flowing. It was presented in 2018. So that's the mesh, even more finer mesh for the flow. And again, you solve magnetic field with ANSYS. This is only the fluent mesh for the flow. And because it's very detailed, you can see the impact of the channels on the solution. So that's the deformation. That's the height of the deformation. That's the intensity of the flow. So all those solutions, they are steady state, and that's unfortunately not an indication of stability. It's only, it's good to know it's symmetric. It's good to know you don't have too much deformation, but it's not telling you this cell is stable at that ACD, for example. So for that, you have to have another type of calculation. So historically, if we go back, when Virata developed its first calculation of entity, first calculation of flow, after that, he also developed the first analysis, perturbation analysis, or a linear stability analysis, where you take the solution, the steady state solution, and you see how stable that the system is by doing a perturbation analysis. So the first one, this picture is again from Murata, 76, and then Pioneer also Celi, similar work. And this is those two slides are from Celi. So you have parameter like metal pad thickness, ACD, and so those two. So this is ACD, this is metal pad thickness. This is intensity of the BZ. So from 40 Gauss here. But if you have 40 Gauss of magnetic field, you need 20 centimeter metal pad, and you have 10 centimeter here of something, not ECD for sure. So unfortunately, I cannot really use that information here, but the principle is that the more BZ you have, the more ECD is required and metal pad to get to the limit. So those curves are stability limits according to this model. This kind of stability analysis was improved. So Hirata in 85, he presented a new improved version of his work. And here you could compare the prediction of a wave. So a wave mode will be the T wave mode that is more unstable. So it will be the first one that will appear. So the cell will normally use that mode unless you can activate or a different mode, but normally the most unstable mode will appear first. So this is there's a given frequency for that wave and a given shape for different phase of the wave. And so this is a prediction from the stability analysis code from Hirata, and then that's measurement from a real cell. And then Alcan, when Hirata published that paper, Alcan, I was working for Alcan at the time, and Richard Boivin recoded that Hirata model. And then another of my colleague, Frédéric Laroche, did this master degree in measure wave in cells, and then he compared the Hirata model prediction, recompiled by Richard Boivin, compare with his measurement, and then we got a very good match. So that's confirming that that this model was very good to predict the wave shape and the frequency. And that was also a way to predict the stability of the code, of the cell. And here we have an example from Jacques Antti that was at the time after the move from Suisse to Alcan. He was working at Alcan when he presented that paper, where here he presented a linear stability analysis result, and you have a prediction of unstable cell at that frequency, and then here you have measurement of the same frequency in a cell. So here we don't have a comparison of like previously of the shape of the wave at different time in the wave cycle. We simply have a direct comparison of the predicted frequency for the unstable cell and the measurement of an unstable cell at that same frequency. Okay, there's a lot of flavor for those linear stability analysis. Here we have the first three I presented. So the initial Hirata, CELI, and then the second Hirata. There's more, and then the very most recent is from 2018 from Bojarevich. And here we have incorporated the friction into the linear stability analysis. So now we have a true prediction of instability at 0. And we have the displacement of the mode, the eigenvalue. We are displaced based on the action of the friction coefficient. So this is the mode that is now predicted to be the most stable here. After previously, we normally without friction, all those modes below 0 should be unstable, but they displace the threshold for instability, try to account for this limit of stability, considering the action of the friction. But now that is incorporated, it is truly 0 is the limit for stability. Okay, so that's now to avoid to have to solve for this linear perturbation analysis. You can also try to solve the code, the flow problem in transient mode, like it has been done here by Valdez. But to be able to do that, you have to reduce the size of the model. And that's what Valdez is doing. I will show exactly how. So we'll go step by step. First, to solve the current density, instead of using full 3D element, the code is using linear 1D element for most of the calculation of the current. Here you have the cathode block, the collector bar, the bus bar, the anode pin, and we have multiple cells, so we have multiple time configuration. So you solve that mostly using linear element. So you can reduce the size of the model this way when you compute the current density in the liquid zone. And not in 3D, in 2D only. So this is one solution that will in the middle of the metal pad. For the magnetization, for the magnetic field, you don't solve it using finite element. You solve it using boundary element formulation. So you don't have to mesh the air. You don't have to mesh anything except the bus bar and the ferromagnetic element. So in this case, the pot shell and the anode superstructure. And you only have to compute the magnetic field when you want to know it. So in this case, in the middle of the metal pad, in the middle of the back, on the middle of the ACD in the back. So you have two magnetic field, two 2D calculation of the magnetic field. And you have the magnetization to solve. So here you have 3D element for the steel. And you have the bus bar that are still the solution from the electric. So 1D linear element. So from that you get the Lorentz force and the metal pad and the ACD. And then you have the flow, so the bed flow and the metal flow. Still all steady state initial solution. And then again the Lorentz force, and this is the deformation of that metal interface. So I'm showing the Lorentz force compared to the deformation because you have here you can see the relationship. If you look here before, you cannot guess from looking at those the two fields or the force what kind of flow you're gonna get, because what put the flow in motion is the divergence of that force field. But for the rotational of the force field, but the divergence part of the force, that is the dominant part, will create the deformation of the interface. So here you have you pushing from upstream in that direction, from downstream in that direction. So the maximum here, we don't have force here. It is the maximum height of the back metal interface deformation. And here we have the maximum force pushing away from the wall, so that's why you have the minimum height here. On the upstream side, you have more force than the downstream side, so you have a lower level of metal on this side compared to the other side. And I could explain why you get this magnetic field, this force field, but I don't have the time, so sorry about that. Okay, so now you have the initial solution, steady state, but this code is can compute fairly quickly the steady state compared to the full 3D. So now you can afford to trigger the transient mode, and then you kick the wave, so you displace the wave, the steady state solution, you displace it to introduce a perturbation. And you let this perturbation die out. In this case, when you have a stable cell, the initial force perturbation will die out. The decay rate is exactly the stability index that you get from the linear stability calculation. But this could be fully nonlinear or partially nonlinear, depending what you recalculate every time step. You could recalculate everything, or you could recalculate only the magnetic field and then the force, or you could recalculate everything, or I mean the current density and then the force, or you can recalculate the current density, the magnetic field, and the force, and then you evolve with that, the flow. Every level, the more you go nonlinear, if you go full nonlinear, then you have the maximum time to compute, but the most accuracy. And then, so you get, so the dying out or the amplification of the perturbation is the stability index. So when it's negative, it's stable because it's dying down. If it's positive, then it is increasing, then it's unstable. And then the frequency, but you analyze this wave and then you get the mode from the Fourier spectrum. You know the frequency of the wave. Okay, so that's it for MHD. Next. So we need to go faster. So this is a bubble model. So that was pioneered by JNARDDC. So this is a physical model. This is another by Chen in Oakland University 20 years later. Now you can see the picture because this was published in JOM. So you have the bubble that are generated by, you inject some air, then you have the two-phase there, and then you have the bubble, and this way you can study physically the effect of the bubble flow. And then the very pioneer for the calculation is Solem in Norway, 89. And then Severo for Kaiti, Brazil. The full 3D solution with only the bubble flow or mixing with MHD flow. So 2007 this time. And then you need to validate this. And so this is CSIRO, the thing at CSIRO. They have the apparatus to measure the flow. And then they use this measurement to calibrate their model. So before calibration, the flow was too intense. And then after adjusting the turbulence model, we could match their measurement. Another type of measurement you could do from Professor Gao from Northeast University. So it is a cell with some transparent wall. You can put camera on the side or below. In this case, we have picture from below. So you can have here 3 cycles of wave bubble formation. So you get bigger, and then the bigger bubble escape. So you're back to this situation, and then bigger, and back to this situation. And the frequency is 2 seconds. So on the period, so the frequency is a fraction of Earth. In real cell, it's more like 1 Earth is the frequencies. But this is the same principle. The bubble form, they get bigger by merging, and eventually the biggest one is unstable and escape. So the type of model that you can have. So this is the VOF, volume of fluid, fraction of volume of fluid, and DBM is a discrete bubble model. So discrete mean particle. So up to the point where the bubble that they form under the anode, they are so small that you cannot resolve that the mesh will be too fine. So they are subgrid. They call it subgrid bubbles. So they are maybe 1% of a single cell, and they are represented as particles. And then those particles, they are there. They can merge, they can get bigger. Eventually, you get a particle that is so big that is about the size of the mesh. So then you transfer the representation from the particle to the volume of fluid. So you have a 2-phase. So this is a bubble in the middle, represented by a second phase in the VOF formulation. So we have converted from this formulation to this formulation, the same bubble. And then, so those macro bubble, they can merge small bubble to get bigger, so they can merge between themselves. So this bubble and this bubble merge from a single bigger bubble. And you have here the same cycle, so you have small. Now we only see the macro or the big bubble. So they grow, this one escape, and then go back to this. And this cycle is again should be matching the frequency you observe in your real cell. So this was done by Masroud. In 2016, he had for his PhD. He published in 2016 a paper, but his PhD was done before then. He had a physical model, and then he was recording the voltage fluctuation, and then his model was also computing the current, the resistance evolution due to the bubble and the frequency of the voltage fluctuation due to the bubble motion, and you get a good match. That's the way he validated his model. And so, from again, Northeast University, we study in that kind of model the impact of the slot. Because by introducing some slots, you reduce the thickness of the bubble and the coverage, and so you reduce the resistance due to the bubble. And if you have the model can account for that, and then here you can see that introducing those slots reduce the resistance through the bubble layer, as observed in real cell. Okay, so next subject is the alumina dissolution. So here we have Syntef in Norway. They have done some measurement in real cell by injecting something at the feeder location and detecting it in some position around. So they presented this paper in '97. And then Zhang in China, they developed a model that is using particles for the alumina. Yeah, in this model, you have two types of particles. So yeah, you need to have the bubble flow, you need to have the MHD flow, so that's a combined bubble and MHD flow. Then you inject particle, and then you can predict that represents alumina, and then the alumina will dissolve, increasing the concentration of dissolved alumina in the bath. All this is done in that kind of model. Ashwood presented a similar model, more physics, because he accounted for the rounding of the corner of the anode and the shape of the ECD due to the bat metal interface. So the bubble will, of course, they will move differently if the anode is not flat, and if the anode is not square in the corner. But and then so the flow will be affected by that, and then the solution of the alumina injected will depend on the flow. So this model and this model, and also the physics of how the particles are dissolving could be different. And then another physics that is normally missing is the raft formation that was observed. So when you add the 1 kilo or 2 kilo of alumina on the bath surface, it will not sink because the alumina is cold and you want to form a raft. So the raft is after, this is before a shot, and then after 5 seconds after, and then slowly it will dissolve, and then you're back to this condition before the next feeding. So initially you have a big raft or a big lump of floating alumina, and it is floating because the alumina is denser than the bath, but initially it will kind of a insulation made of frozen bath will form a kind of a shell, preventing the alumina to essentially sink into the bath. And when this thing remelt, then the alumina finally get into the bath. So here we are kind of trying to simulate that. Roger in 2021, so very recently, we have a model trying to predict this exact physics of adding cold alumina particles. They get hotter when they touch the bath, and then eventually they sink. And this Kazas, she did a PhD trying to observe this using physical modeling. So here we have a physical model where you have you inject some cold particle into this liquid, and then eventually form a raft. Eventually, the raft, disperse, and then the particle can drop down. And that's the interface, black metal interface, or equivalent for this physical model. So essentially, the raft is a view from underneath is a cloud, and it's dropping eventually particle. Those particles that are denser than the liquid, the first liquid, that is the bath, but not necessarily denser than the metal, so the second liquid. So most of it accumulates at the interface before eventually dissolving. So it's a three-step. First step, it's a cloud, then the kind of a snow. So the particles drop, accumulate at the interface, and then dissolve at the interface, if they are not going straight through and making sludge. And then you have backfeeding. But we are not there. We only try to represent the first three steps. Here we have an first, again, Boyarovich, very recently, 2022. He was able to simulate the full physics using this shallow layer or shallow water. And you have the physics of the raft, because we are the large particles, they are rafts, so they are floating on the surface, and they cannot move freely. They have to stuck to the channel, and eventually they dissipate into smaller particles that will move around and dissolve. Okay, let's go fast. So multiphysics is the next. So you merge all those four, and then you get multiphysics. And but you have a challenge of scale. You have a very small micro bubble, so millimeter or even less than a millimeter in size, up to a full size of a smelter, because you have the magnetic field. You have to account for the full smelter contribution of if you push it to limit. So you have that. So you have to cover that scale in space, and then you have a very fast event that 10th of a second, up to a full anode cycle change that lasts hours in this case. So you go from a fraction of a second to hours, and you go from millimeter to hundredth of meter. And you have to solve essentially 4 parts of physics. Here in this paper is covering only 3, but you have to solve for the magnetic field. You have to solve for the temperature, so the thermal field, the bubble flow, and then you have the chemical field, that is the alumina. If you merge all this physics, then you have a full multiphysics model. The one that is in development, it is already being used for designing, but it's very, very slow. It's called ALUCEL, developed by Lausanne University for now Rio Tinto. And so it's solving in this representation here in 2018, solving 3 out of the 4. So the MHD, thermoelectric, and alumina. The bubble is missing in this presentation. So it's full 3D, trying to solve all the physics, and it is so it's accounting for the MHD solution on the ledge formation. So you have and then the temperature results on the point shell. You have less metal on this side upstream, so you have a colder side, and then you have more metal on the downstream, so you have less ledge and a hotter sidewall. You have also the result for the alumina feeding from the flow. And so this is already 3 out of the 4 field, and this is adding the bubble. So very, very recently, a PFL, that is University of Lausanne, they developed the bubble flow that will be added to ALUCEL, and then eventually they will have a presentation where they are mixing all 4. Okay, now moving very fast to all the remaining. I will have to cover the last in 10 minutes. So this is the thermomechanical. So you have you want to predict the deformation of the pot shell. The sodium is expanding the cathode block, and then depending on the grade of cathode, there will be more or less expansion. The graphite expand less, and the amorphous expand the most. So those are the three lines in this model. But every single material, the more you push on it, the less it expands. So you have here one material, but you're applying more and more pressure, so the expansion is reduced. So if you combine those two things, different material, different pressure, you have those different slope here. But according to doing, the slope is about the same. So regardless of the material, the effect of the pressure is almost the same, represented by this coefficient. But the free expansion then depends on the material. So that's the Doing law. That is pioneered by Doing for this calculation. The very first work on this physics is from Rappaport 57, but it's not a model. And Doing, it's not such a model. It's only a law, physical law that we have. Now you can use this law, Doing law, into a model. But before that, it was some physical modeling, or in that case, they built a small scale cell, one block, to study it. Reported in June 69. And for the modeling, I was maybe the pioneer, I'm not sure. But in 93, I incorporated the Doing law as a boundary condition on this model here. So I'm applying the pressure based on the Doing law, and I get the response from the structure. So I transfer the load through the lining to the steel structure, and I'm getting an equilibrium based on the expansion from the Doing law inside, and then the response from the shell, the pot shell. So it's a stiffer pot shell will get more load. And then you establish the equilibrium. The pot shell could be 2 weeks and then deform plastically, so you have to account for plasticity in your model. And then you have here from result from some TMS 2004 from Norway, the group from Oye. And then we have as for part of GéniSim, I've represented again. And here you have the model is expanded to have the cathode block, and then the sodium is diffusing with time more and more. So you have the Doing law expansion is now in the carbon itself, in the cathode. And this was so big at the time that I could not solve that at Alcan. Even the supercomputer was taking weeks to compute this, but I was able to in 2009 to solve this. The full 1000 day of sodium diffusion and then deformation of the pot shell. The next physics is potential ventilation. So that's my PhD work. So that's my physical model. From this physical model, I was able to get the temperature in the pot room, and then the smoke or concentration of the smoke and the flow. And that's my best solution from my CFD code that I developed myself, in-house code. In this code was using K epsilon for the turbulence model, and it's not matching perfectly the observed flow. But in 93, I was able to perfectly reproduce the observation by using a more advanced model that is called second order anisotropic, meaning that the viscosity or turbulence is acting differently in different directions. In this case, because you have natural convection, you have more turbulence in the direction that is opposing the flow, so the vertical direction. And that's mean that the air that's coming from the side on the window here cannot push the flume, the plume, as it was doing here in the K epsilon. The side flow air push. So we have a 45-degree ascension of the air here, and the temperature is gradient is still big here, bigger than it was observed. But with this turbulent model, we have exactly matching all three things: the direction of the flow, the intensity, and then also the dispersion of the heat above the pot. Now, for application, we have a result from Hatch. So here we have a full smelter. You have dominant wind coming from one direction or another direction, and then that establish the flow and the dispersion of the pollution. And in this case here, you see the pressure field. So the wind is coming not from this direction, but from the side direction, that is this direction coming this way. So you have a positive pressure on this those silo and then this building here and the first pot room here. And from this solution, you can apply boundary condition for this kind of inside model, inside the pot room. We have the temperature solution, and here you have the concentration of HF coming from a butt in this box and coming from the pot in this corner, And then you can solve for like I did and presented this in 2017. I have here a combined thermoelectric and a CFD. So I'm solving for the temperature. So temperature of the panel, temperature of the superstructure, from the heat coming from the pot, and then the source is in the hole here. We have opening from exposed to the bath, so we have source of HF coming from the surface of the bath, and then it wants to escape through the docking system. But if there's not enough negative pressure, it will also be able to escape to the pot room from the hole around the rod or the space between the panel. In this solution, there are no escape, everything is captured. And then you should reduce the draft, and then so you have less negative pressure, you will have some escape. So that's what we try to predict with this kind of model. Next type of model is thermoelectromechanical, pioneered by Daniel Richard, working now for H, but this is it's masterwork. So this is the stub, this is the cast iron, this is the carbon, and this is the voltage solution. And the drop between the cast iron and the carbon is the contact resistance. And this model is predicting the contact resistance based on temperature and pressure. This is the fit from the experimental data that you incorporate into that model. And I reproduced this thermoelectromechanical modeling work. I presented that in that paper at TMS 2010. And Shao and I, we have developed a solution for trying to get pressure from the bottom and getting to pass some current down instead of 100% from the side. Here, there's no current going down because there's no pressure. Same for this model. So any design right now, you don't have any pressure from the bottom face, so you don't have any contact. So no current can flow from the stub straight down. You have to go to the side. But if you can manage to apply a pressure, and here we have done that by having this machining the shape of the hole to have this taping, and then we have machine a ring around the stub, and now we can lock. So the cast iron is locking to the carbon. It cannot move up because of the shape of the hole, and then the cast iron is locking the stub. The stub cannot move up because the cast iron is locking, preventing it to move up. So by a combination of this shape and this 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 geometry here. You can, the vertical displacement is locked. So the stub is applying pressure on the carbon. Then you have a contact pressure, and then you have some current can flow, as predicted by the thermoelectromechanical. So the same law, we are applying the same pressure and temperature dependent connection at the interface. Okay, next is a transient thermoelectromechanical model. So this is a preheat. So this was too big. In 1994, when we developed this model at Alcan, it was solved on a supercomputer, and even then it was taking a lot of time to get the full 3D solution evolving with time. And from the temperature, you can calculate the stress, and then it was to solve an issue about this geometry here. This smelter was having a lot of early failure. So the first block was cracking in the middle here, as predicted by the model eventually, and we found the cure based on the modeling work. And Archipol, with TMS 2011, presented similar preheat model with the gas preheat. So you have the gas solution, and then you apply from the gas, you apply boundary condition to get the temperature in the lining. And from the temperature, you can get the stress in the lining. Here that we have the displacement for X and Y and Z displacement. Okay. And then reverse, when you stop a pot, it's cooling down. And then here you have the simulation of the cooling down. And from that gradual decrease of temperature, you will eventually get some stress in the cathode block that is being now computed or displayed in this side. And there are two independent calculations because it's we are not accounting for any nonlinear behavior, so we are using only the temperature. And here we have a linear modeling of on the mechanical side. And we are reaching to a point where we are getting 9 megapascal. That's enough to crack the surface. So the model here is predicting cooling cracks on the cathode surface. And the next type of model is from Hatchworth. It is a combined thermoelectric and CFD in bus bar. In this case, a bus bar in a tunnel. So if you only let the natural convection, you may not get enough ventilation, and you have a too hot bus bar. When you start to push some air inside, then you cool down your bus bar. So this is a solution of the airflow and the temperature due to the Joule heat from the current passing in the bus bar and the temperature of the air. So it's a combined CFD for the air and thermoelectric for the bus bar. And once you have the temperature of the bus bar in the tunnel or elsewhere, you can have the detailed mechanical calculation. Here we have a stress prediction for the welding of plates. So you have some thermal expansion creating some displacement, and those displacement are generating those stresses. And here we have a safety factor, and we are exceeding the safety factor when we have like green here is quite low, below 1, and way too low, so it's prediction of cracking of this weld. And here in the end, simply replace the stacking from vertical plate to horizontal plate stacking, and that's reduced for the same expansion. You're getting way less stress in the weld. And here we have the model calculating the multi-contact of flexible. We have some cycle of expansion and contraction, and they have done this exactly same cycle into the wilting. And now we have a comparison of what they have observed and what the model is predicting. So here it's very nonlinear because each plate or sheet of aluminum can contact its neighbor. So they have 100 of potential contact point, and they can open, they can close, and then it's transient. So it's a very advanced modeling. And as you can see, they got a very good match between what was observed and what the model is predicting. And as the paper explaining, to get exact match, you have to change a bit the angle of this bus bar. So less than 1 degree made a lot of difference in the solution of the model. And the last model is the lump parameter model. So I'm almost done. Sorry for extending a bit. So the lump parameter means you represent the full. You want to have a transient model to predict evolution of the cell. So it's a cell simulator, dynamic cell simulator. You have to reduce the size. So in 1980, the very first lump parameter model, lump means every piece is 1 temperature. So I know there's 1 temperature cathode plug, the ledge. And so you solve for the evolution of the temperature for all those lumps, and you get some prediction of resistance and etc. And then you can compare with the observation. So the second one that was developed by Kaiser based on the PhD from the right and was done to commercialize or advertise the central cell controller. And then you have one from KT, because Bertie was done his PhD for KT to develop a dynamic cell simulator. And then Jacques developed one for Canada 2015 using MATLAB and Simulink, so a different representation. And me, I developed mine not as a PhD because I did already my PhD, but for myself. So I presented the first result 1996 here, and then in 2007, Ingo Hike from Hydro presented the comparison with measurement with me. And then this is a picture of the cell simulator. I reran the same case to display some other variables. And then you can evolve that to multi-zone. That means that instead of having 1 lump for the bath or 1 temperature for the bath and 1 concentration, and then you can divide this in zone, and then every zone will have its own concentration of alumina, its own temperature. Apart from that, the same model, same type of approach, lump, but different number of lump, more lump essentially, but in the back. And so you have a solution here from Wong, from New South Wales University. So different temperature, different alumina concentration. Yeah, you can see the fever. Same model, but now it's showing different paper, but the same model, same work. And yeah, this is the alumina concentration. And you can try to match with observation. And because the goal is digital twin. So this is the digital twin. You have a cell simulator. And now you want that cell simulation to match your observation. So you have to do something to synchronize it. And something is a Kalman filter. So in this sketch, it's not clear. The Hydro presented again in 1980, showing another sketch, but the same concept. And then again in 2010. So this is the nicer sketch. So I'm going to use this one to show what is occurring. So we have the real cell is here, the process. You get some output, so measurement. voltage, amperage, temperature if you measure temperature, but chemistry if you measure bath chemistry. So you feed this here, and you have here you're running a simulation. So you have a cell simulator that is initially disconnect completely from the real cell. But here you're comparing the output from the real cell to the output of the model, and then there's a discrepancy, and then you try to minimize by recalibrating your model. This loop is simply like you have a weather model, and then you're readjusting the input of the model, so it's starting with the current condition to predict the future condition. So here you're running this loop continuously. And so this you essentially, by running this loop, and this is the Kalman filter, or the way to compare and readjust the model. Can be different style, different algorithm for doing this work, and then they are more or less efficient. So this one is very efficient because very rapidly it's there's a match between the prediction of the model and the measurement of the real cell. And once you have done this, you have your simulation is no longer a simple simulation. It is now a twin. It is a duplicate of the real cell. And this duplicate can now be used to predict the future state of this real cell. So you feed those predictions to the controller. So this is the controller here. So this is what Hydro is doing in his technology Hall-4E and Hall-4E Ultra. And it's using this exact type of controller to better control the cell. And according to what they have reported, they can reduce the number of exception pods, so the number of intervention, by a factor of 10. And of course, they are not only gaining in the manpower here, but they're gaining on KPI, but they are not reporting the gain of KPI. But if you reduce by a factor of 10 your number of the exception pod, so the pod that are too cold or too hot or have problem with feeding or whatever, that just can go wrong, because you can detect the deficiency quicker, or you can prevent the pod to go too hot or to get too cold. Then you're gaining a lot of productivity. And then the ultimate will be to have a multi-zone digital twin, where you can use the information from individual rod measurement to prevent anode defect faster. And most probably this simulation here and that Hydro is using is not multi-zone. It's a single zone for the bat. And that was so they're working on a multi-zone Kalman digital twin in for a future cell controller. So that's it. Thank you very much for your attention.
Thank you, Mr. Marc, for the excellent presentation. Participants, if you have questions, please unmute yourself and ask. Mr. Marc, there is a question from Lipak Sahu. What kind of models were used for capturing interface, multiphase models, and modeling flow turbulence in CFD model?
Can you repeat the question, because I was distracted? I could not unmute myself.
Yes, sir. Yes, sir. I repeat. What kind of models were used for capturing interface, multiphase models, and modeling flow turbulence in CFD model?
Well, that depends who is developing the model. What I explained in my presentation, several way to do it. The one way is to use ANSYS to compute the force, compute the Lorentz force from and then you go to a CFX or Fluent for the CFD in 3D, or you use this commercial code, in-house code, but called MHD Valdis, that is solving in 2D the flow and solving the bat metal interface. Or there's more option, like a third option that I was not discussed in that presentation is Esther Phoenix. And you eventually could use open foam. So there's no real limitation of which type of CFD code you want to use. The CFD code must be able to solve for two-phase flow to track the interface, to track the bat metal interface. And you need to find a way to compute the Lorentz force. So so you need to compute the magnetic field, compute the current density. And typically it's not done in a CFD code, so you need another code. And the most popular one is ANSYS, but it's not the only one you can use, because MHD Valdis is not using ANSYS to compute the magnetic field. It's computing it itself by using a boundary element formulation. So there's many code.
Okay. Anyone want to ask questions? Please ask.
Hello, may I ask you one thing?
Yeah, go ahead.
Yeah, and thank you very much for your very interesting but very difficult modeling for me. I am an alumni engineer. From your presentation, nowadays there are many, the cell is getting bigger and bigger.
Yes.
And if you point out very important key issue of to improve electrical efficiencies or something, what alumina should I prepare for the cell from your viewpoint of cell simulations?
What type of alumina you're asking?
Yes, the solution rate, particle size distribution, or
I'm not an expert for this. I'm a modeling expert. So no, well, there's some spec for alumina that are well known. I don't know them by heart, but you need an alumina that is easy to dissolve and will not float on the surface, or less as possible. So normally you don't like too many fines, new alumina, and then there's all other aspect but I'm not the expert to ask that question. Me, I'm trying to model whatever the physics, like the thermoelectric or MHD or alumina dissolution is another thing, but alumina dissolution is a more recent activity, and it is normally we rely on some measurement of alumina dissolution from lab to get the dissolution coefficient constant. And what is a good alumina? What are the good spec for alumina? That's not my expertise. Sorry about that.
Thank you very much.
There is one question from Amit Kumar. Can FEA analysis predict pot life?
Yes, to a point. You can predict erosion. That's a type of model I have not presented in the presentation, but I also have modeled that. You can predict the erosion pattern, and then gradually erosion with time, and then eventually the thickness of carbon above the bar would get to zero, and then that's a prediction of failure of the pot. And I have a paper about that that I published maybe 20 years ago. So normally these now the pot life is controlled by the erosion rate. So the time it takes to get to erode all the carbon that is above the bar, and there's a and that's typically now 5 years or something like that. So 2,200 days or something. That's but before that, when we were using anthracite carbon block, we were getting 3,000 day and more pot life because the erosion rate was less. If the pot failed this way, then that's we can predict this pot life by erosion. But we rely on the erosion rate that is measured by measuring the erosion pattern through autopsy or by live measurement during operation. And then we input that parameter into the model, and then we let the model predict the erosion, future erosion of the pot. So that can be done, yes.
Okay. Any questions? Sir, it's look like we have covered all our questions. Is there anything else you wanted to cover before our wrap up?
Well, I thank you for the opportunity to present this. And then if there's any other question, you can reach me on, yeah.
Yes, sir. Great. Thank you, everyone. Thank you again for joining us today, and we will see you next time. Thank you.
Okay, bye.
Bye.
Thank you very much. Bye.